Hi, my name is Karan Taneja, and in this video I'll be talking about our paper, Can Active Label Correction Improve Large Language Model-based Modular AI Systems? The co-author include me and Professor Ashok Goel at Georgia Institute of Technology. This paper is being published at EMNLP 2024. With the increasing popularity of large language models, LLM-based AI agents have become a commonplace. Systems like AutoGPT, Gemini, Perplexity, Hugging GPT, and a system we developed at our lab for students called Jill Watson rely on a series of LLM calls to perform complex tasks. These systems use LLM capabilities for many subtasks like perception, planning, task decomposition, tool use, and memory management. But there are three main problems when it comes to LLM based AI agents. The first one is that AI agents are limited by the performance of the underlying LLM. And there are limited options to improve these LLM-based agents. One might hope to improve these models as new LLMs are released, but it has been shown that AI developers cannot simply rely on improvements from LLM updates because they can perform worse over time on complex NLP tasks as they're fine-tuned for safety and conversationality. The third problem is that errors in large language model based AI agents propagate through the modular system and lead to compounded effects on the overall performance. For example, for the system shown here, the overall performance is lower than 50% even when all the modules are working correctly 70 to 95% of the time. What we learned from this discussion is that we want to take on the challenge of fine tuning task specific models. And for that, we simply need two things, the training data and the computational resources required to train them. So the question we ask here is, can we use the data aggregated by the AI systems to improve itself? Let's consider this imaginary deployed AI system and this one very specific module that prompts an LLM with an API call with whatever input it receives. This model could be an intent classifier, a named entity recognition module, a textual entailment module, or something else. What we can do here is collect these input and output pairs from the data traces of this system, which are stored from its usage in the real world. And the data aggregated by each module of the AI system can now be used to train replacement models for the LLM API calls. There are many benefits to this process. The first one is that there's no domain shift as the data is from the real source, which is the deployed AI system. We can also train smaller models for simpler tasks now and bigger models for more complex tasks. This can also be cheaper and faster than using LLM API services. And the model can be improved over time as more data is collected by the system. Finally, one can also imagine improving the overall performance by a huge margin if they focus on the weakest link in this process. But the main issue, of course, is that LLM annotated data from the data traces can have a lot of errors, which makes the training data noisy for fine tuning task specific models. Now we want to understand the extent of this problem, and to understand the performance gap between GPT 3.5 and fine-tuned models, we took three publicly available datasets and obtained GPT 3.5 annotations for all data points in these. We measured the train and eval performance of GPT 3.5 on these datasets and also measured the performance of models trained on the original data annotations. And we see that there's a big gap in the performance that needs to be bridged if we wish to improve upon GPT 3.5 on the test set and achieve the best or the oracle performance seen from a model trained on clean data. To understand how complex the noise introduced by GPT 3.5 is, we analyzed data projections and errors in low dimensional spaces and found that most misannotated examples actually lie near the intersection or between class clusters, which implies that these are genuinely confusing examples in corner cases sometimes. We also analyzed different noise models that have been used in previous work for evaluating methods for noisy datasets and found that the noise induced by GPT 3.5 is most detrimental for model performance given the same number of noisy examples. In the proposed process, we suggest efficiently fixing the data with human feedback using active label correction. To understand this process, let's start with this AI system and the specific module again with a prompt and an API call. We have collected input-output pairs from the deployment to form a noisy dataset. We shall now use this dataset to predict the examples that are most likely to be misannotated, and then obtain human annotations on a fraction of these examples, and update the labels in the noisy dataset. We do this process iteratively while retaining human annotations from previous iterations, until we see a saturation in the test performance, at which point we have a fine-tuned model that can replace the LLM API call. The basic ALC method involves first training a model using noisy dataset and then using it to predict outputs on the training inputs themselves. The examples with the lowest confidence or the highest entropy are predicted to be misannotated. In dual ALC, we follow the same training and inference process, but additionally resolve disagreements in the prediction and labels by switching labels when the model puts very high probability on an output that is different from the label in the noisy dataset. Again, we consider examples with the lowest confidence or the highest entropy to be misannotated. In ALC3, we again follow the same process as we train a model and perform inference using training inputs. Similar to dual ALC, we perform a step called autocorrection where we resolve disagreements between model predictions and noisy labels. A fraction of the dataset is then predicted to be misannotated, and it is annotated by the humans. We perform an additional filtering step where we remove the examples that are still likely to be misannotated but were not corrected by human annotations, so that we can reduce the noise in the model training. We update the dataset based on these steps and then perform this process iteratively. After training the new model each time, the filtered examples are considered again in all three steps as we perform autocorrections while retaining human annotations from previous iterations, get human annotations, and get a new set of filtered examples before training the model again. We measured precision and recall of misannotation prediction as we increase the fraction of flagged examples for human annotators in different cases. We found that a small fraction of flagged examples per iteration leads to higher precision, but lower recall because we can only cover a small fraction of them. But the overall recall is calculated by adding up recall from all the iterations, so we'll actually improve in the long term by having a greater precision and retraining better models in each iteration after incorporating human feedback. Before I discuss some of the main results, let's consider the number of annotations required with a perfect misannotation predictor to clean the entire dataset. This is exactly equal to the number of examples that have errors in them. In case of ATIS, it's 29.8%, 57.4% for CONLL 2003, 15.1% for QNLL. To give you a sense of the number of iterations it takes to achieve Oracle performance, consider the CONLL data set where we simulate annotating 5% of dataset in each iteration. In this case, ALC3 achieves the Oracle performance shown here in the green band in 9 iterations, which means that we had to correct 9 times 5 equal to 45% of the dataset. We perform this iterative process with each of the methods, including a random baseline where we select random examples for human annotations. We measured the fraction of dataset required to achieve performance within 1% of the fine-tuned model performance, and the results show that in each case the proportion of dataset that needs to be annotated with ALC3 is much less than the percentage of annotations required with perfect misannotation predictor to clean the dataset. It also consistently requires less annotations than all previous methods. But why is ALC3 so effective? The first reason is that fine-tuning of task-specific models leads to an improvement in performance from the beginning because the domain shift is no longer an issue. ALC3 also autocorrects examples, only saving the most complex examples for the human annotator. It also estimates the number of noisy examples and filters examples still likely to be noisy. This noise reduction leads to a boost in the model performance, which in turn improves the misannotation prediction in the subsequent steps. And finally, we should also note that with ALC3, we are aiming to achieve the Oracle performance instead of achieving the perfect dataset. As I wrap this presentation, I want you to walk away with 3 takeaways. First is that your AI agent does not have to be limited by the performance of the underlying LLM. You can train your own models with data collected from deployment of your AI agent. Errors propagate through modular systems, so you can focus on fixing the module with the lowest performance, that is the weakest link. You can use ALC3 to efficiently get human feedback and free your system of the domain shift problem, minimize expensive API calls, and get rid of large language models where they are an overkill. With that, please feel free to reach out to us with your questions and feedback at our emails here, and thank you so much for listening.